So problem 8.4. Write the Taylor polynomial Pn centered at 0 of the function f is equal to e to the minus 1 over x squared when x is different than 0, and it's 0 when x is equal to 0. Okay. So now this function is not defined at 0, right? And so we can get the limit when x goes to 0 of f is equal to the limit when x goes to 0 of this function, e to the minus 1 over x squared. We know that this thing goes to minus infinity, right? So this is e to the limit when x goes to 0 of minus 1 over x squared, right? And this is going to be minus infinity, so e to the minus infinity is 0, right? So this function is continuous, okay? So the function Pn 0 is going to be f at 0, which is 0, right? Plus the derivative at 0 times x, plus the second derivative at 0 divided by 0 times x squared, plus and so on, right? Up until we get to the nth derivative at 0 divided by n factorial times x to the n, right? So let's compute these derivatives, right? The first derivative is going to be the derivative of this, which is the derivative of minus 1 over x squared, which is minus, so plus 2 over x cubed, e to the minus x squared. You can write it here if you want. If x, sorry, this is not f prime at 0, this is f prime, right? If x is different than 0, if x is equal to 0, we can compute the derivative using the definition, right? So we have the limit. Here we have, this is f minus f at 0 divided by x. Okay, f at 0 is 0, so this is the limit of e to the minus 1 over x squared divided by x, and this is going to be going to 0, 0, right? So again, we can compute this using many ways. You can compute this using L'Hopital, for instance. If you use L'Hopital here, you get the limit when x goes to 0 of this, right? But in both cases, you need to evaluate this limit, okay? And the idea here is that e to the minus 1 over x squared goes very fast to 0, and the way to show this is to change the variable t 1 over x. So the limit when x goes to 0 is the limit when t goes to infinity. So this is the limit when e to the minus t squared divided by x, so this is t, right? T times e to the minus t squared, and we know that this is going to be equal to 0, right? Because e to the minus t squared it goes to 0 much faster than t. Okay, so the derivative at 0 is 0, right? Now we can do the same thing with the second derivative, right? Let me erase this part thing here and compute the second derivative, and again from here we get that this is going to be the derivative of this, which is, let's say, this is 2x, this is minus 6 x to the 4 plus and the derivative of this, which is 2, so 2x to the 4 sorry, not x to the 6, sorry, this is a square, right? 4x to the 6 e to the minus x squared when x is different than 0, right? And again, using the same argument, we can reach that this is 0. We can reach the second derivative at 0. Again, using the same argument as we have done, we can compute the limit and we'll reach this is 0. Okay. So, and if you can keep doing this, it seems that this is going always to be 0, right? Because the derivative, then all the derivatives are going to be something that's, you know, a function of 1 over x to something times e to the minus x squared, right? And this is going to 0 much faster than any polynomial expression that we can write here, right? And a way to show this is to prove using induction that the nth derivative is going to be a polynomial in 1 over x, right? So this is a weird polynomial. Instead of having x, we have 1 over x, right? Think about it. If you think about the variable t, right, equals 1 over x, then this thing is minus 6t to the 4 plus 4t to the 6. So this is a polynomial in t, right? So this is what we are meaning by this. A polynomial that's multiplied by this e to the minus x, right? And in every case, the limit at 0 is going to be 0, right? So how do we show this? Well, this is certainly true for n equals 1, right? And now how to prove it? Well, we differentiate this. What's the derivative of the nth derivative is just the derivative of the first element. So this is Pn prime times the derivative of this. So this is minus 1 over x squared times Pn prime of 1 over x times e to the minus x squared. And then plus the derivative of this, which is 2 divided by x cubed times Pn divided by 1 over x e to the minus x squared, right? So again, we have e to the minus x squared that's multiplied by, and these two things are going to be polynomials, right, in 1 over x. So this proves this induction hypothesis, and the limit, it's also going to be 0. So this is the limit when x goes to 0 of fn at x divided by x, right? And so this is, if you have this is the limit, and we can change again the variable to t1 over x. So this is the limit when t1 over x of t times pn of t times e to the t squared minus t squared. So this is e to the minus x to the minus 2. So I've been writing it wrong the whole exercise, right? So this is e to the minus t squared, and we know that no matter how high or great degree the polynomial expression has, this is going to infinity slower than this is going to 0. Okay, so this is going to be 0. Okay, so all of these derivatives are going to be 0, which means that the polynomial of nth degree center at 0 of this function is going to be 0. Okay, and so that means that this function cannot be approximated by a Taylor polynomial because at 0, because the remainder, okay, at this particular point, it's not going to converge, right? The remainder is always going to be equal to the function. Okay, so it's not going to converge to 0, which is what we want for Taylor expansions, right?